Let us start today's class. So here we have discussed, I'm in the process of discussing balance equation of shear and bridge. So we have completed in previous class the measurement of capacitance using shear and bridge. Now let us continue with that. So what are the limitations of shear and bridge, low voltage shear and bridge? The calibration for the dissipation factor is very much useful only for the value of one particular value frequency. So if you want to use for other frequencies, a correction has to be made by multiplying with the frequency ratio. So whatever the detector you are using here is not so sensitive. That is one more disadvantage. And to obtain the balanced condition for this bridge, for the shear and bridge, is quite difficult, it's challenging. Finally, the errors are present in the measurement of small capacitances. It's very much not appreciable because you are measuring the unknown capacitance. If the value of the capacitance becomes less, then errors will be introduced. So it's not that accurate for the measurement of small capacitances. So what are the advantages? As C1, which is equal to R4 C2 by R3, and C2 and R4 is fixed, the dial of R3 may be calibrated to read capacitor directly. This is one of the advantage. Suppose for fixed frequency, capacitor C4, dial of capacitor C4 can be calibrated to read dissipation factor, which is directly as D1 is equal to omega C4 R4. So difficulty, we already, limitations already told that apart a simple disadvantage only with the tuning here, a difficulty in obtaining balances R3 appears in both the equations. These are the advantages and disadvantages of shear and bridge. Next, we'll come to the shielding and grounding of bridges, that is last topic of this chapter. The various bridges, what we have discussed until now, consists of the lumped impedances which do not interact in any way. So in practice, the stray capacitances between the various bridge elements and ground and between the bridge arms themselves exist. These stray capacitances shunt the bridge arms and cause considerable error in the measurement. The stray capacitances are uncertain in magnitude. They often vary with the adjustment of bridge arms and position of operator. The shielding and grounding of bridge is one way of reducing the effect of stray capacitances. But this technique does not eliminate the stray capacitances, but makes them constant in value and hence they can be compensated. One very effective and popular method of eliminating the stray capacitances and the capacitances between the bridge arms is using a ground connection called Wagner ground connection. This is the diagram, what I'm writing here, what I've written here, what I've shown here is Wagner ground connection. So the connection you can see here. The circuit is a capacitance bridge where C1 and C2 represent the stray capacitances. The Wagner's connection is the use of separate arm consisting of the resistance Rw, you can see here, and the capacitor Cw across the terminals C and D, forming a potential divider. It forms a potential divider, these two. Can you look at the diagram? This arm is also called guarding arm. The procedure for the adjustment, let us discuss one after the other. First, the procedure is the switch S. Look at the diagram, understand. Switch S is connected in series with the detector, yes or no? Yes. The switch is connected to position 1 and R1 is then adjusted to get null response, that is minimum sound in headphones. The switch is then thrown to position 2, which connects the detector to the Wagner ground point. The resistance RW of the Wagner connection is now adjusted to get the minimum sound. The switch is again thrown back to position 1. There is some imbalance present now. The resistances R1 and R3 are then adjusted to get the minimum sound. This procedure is repeated till a null is obtained on both the switch positions 1 and 2. This null obtained at both the positions indicates that the points 1 and 2 are at the same potential, but the point 2 is at the ground potential due to Wagner ground connection. Hence, points 1 and 2 are at the ground potential. Thus, the stray capacitances C1 and C2 are effectively short-circuited. Thus, they have no effect on the normal bridge balancing. There are capacitances existing from point C and D to ground, but the addition of the Wagner ground connection eliminates them, as current through these capacitances will enter through Wagner ground connection. So one key point you should remember, students, as the addition of Wagner ground connection does not affect the balance conditions. The procedure for the measurements remains unchanged. Got it? This is how shielding and grounding of bridges is done. So coming to numerical, so we'll discuss few numericals problems. You can see here 4 impedances of an AC bridge in ohms are given. Z1 is given, Z2 is given, Z3 is also given, Z4 is also given. Find out whether bridge is balanced under this condition. We know at balanced condition, Z1 into Z4 is equal to Z2 into Z3. We have written here. So now we got LHS is equal to RHS. Correct? Applying second condition, 50 plus 20 is equal to 70. 40 minus 50 is equal to minus 10. It indicates that the bridge cannot be balanced with these impedances. Understood? So 2 more numericals have given. So please copy down and you have to work out these 2 numericals. So this completes today's class.